Let's unpack this. We are diving into a concept so massive, so fundamental, really, that it makes the biggest, most colossal number you can possibly imagine look like. Well, like pocket change.
Yeah, absolutely. We're talking about infinity.
Exactly, infinity. And for millennia, thinkers, philosophers, mathematicians, they've all wrestled with this idea, this boundlessness.
What happens when you just keep counting forever?
Right, or where does the number line actually end, if it even does? Or, what happens when a sequence just refuses to stop?
Mm-hmm. Our sources today really dive headfirst into that monumental question. Is infinity actually a number, something we can calculate with?
Or is it fundamentally something else entirely, like a conceptual placeholder maybe?
Yeah.
A label for an eternal state.
That's the core of it.
So our mission brief for this deep dive is to analyze the really rich mathematical framework in your sources.
Yeah.
We're going to try to figure out precisely why this boundless concept, well, it fundamentally refuses to be just another number.
Even though it's absolutely crucial for so much math, right? Calculus, geometry.
Totally essential. So we really want to give you, our listener, that comprehensive understanding, the difference between just really big and truly boundless.
And, we're starting this whole investigation with a pretty crucial insight. It's right there at the beginning of the material we looked at.
Yeah.
Because while we're going to spend, the better part of the next hour exploring the philosophical depths, the mathematical complexities, the immediate answer, the sort of core truth, is this. No, infinity is not a number.
Right. That's the headline. The definitive conclusion we have to work from.
Exactly.
Infinity is not a number. It's a concept.
Yeah.
Used to represent what? Undefined?
Please.
Limitless.
Pretty much. Undefined or limitless. And that really sets the stage for everything else we need to explore.
Especially why? Why does it fail to meet those strict criteria for what we even call a number in the first place?
Precisely. Which is where we need to start, really, laying that groundwork. So, yeah, to get why infinity is sort of outside the club, we first have to clearly define the club itself, right?
The number system.
The number system. What exactly is a number, and what does it need to be able to do? What are its, behavioral requirements?
It seems almost too simple when you first think about it, doesn't it? I mean, we use numbers constantly, all day long.
We do. But when you strip away the everyday use and look at the actual structure, the number system is the bedrock. It's fundamental.
And your sources define it as what? A collection of symbols.
Basically, yeah. Symbols are digits, 0 through 9 in the decimal system we use most often. And crucially, a set of strict, agreed-upon rules.
Rules for what?
Rules for using those symbols to represent actual numerical values. Placing them on a number line, conceptually. And the real elegance is in those rules. They let us take just 10 symbols, 0 to 9, and create this infinite sequence of integers and real numbers we rely on for everything.
But the key thing, the functional requirement, it stays the same no matter how big the number gets.
The number must possess a definable, quantifiable value. That's non-negotiable for being a number.
And the practical use of this system is just immense. It covers everything from the mundane, like
counting chocolates left in a box.
Exactly. Or balancing your checkbook, figuring out ingredients for a recipe, all the way up to super complex stuff.
Like astrophysics, engineering tolerances, quantum mechanics.
It's basically the universal language for talking about magnitude, about measurement.
And what's fascinating, as the sources point out, is how adaptable the system is. It's not just one single thing. There are numerous types of number systems.
Oh, right. Like binary.
Exactly. We're most familiar with base 10, the decimal system, where each position is a power of 10. But computers use base 2, binary, just zeros and ones.
And there's octal, base 8, hexadecimal, base 16.
Right. Different bases, different symbols maybe, but they all operate under rules.
So if I'm getting this right from the sources, whether you're using base 2 or base 16, the rules for how you represent things change, but the core purpose is identical.
Precisely. They all exist to designate a finite, measurable quantity.
Okay, finite, measurable quantity.
Which brings us right back to that fundamental role of any number, whatever its base. It has to denote a quantity or a value.
If something wants to be called a real number, it needs... What were those two characteristics again?
It must possess two specific measurable characteristics, magnitude and measurement.
Okay, let's break those down a bit for the listener. Magnitude. That just sounds like size, right? How big something is.
Exactly. Magnitude is its size or extent. You can point to, say, 3 apples and say 3. That's its magnitude. You can describe the mass of a planet and give it a value.
It's quantifiable compared to 0.
Right. Every real number, even tricky ones like fractions or irrationals like pi, has a fixed magnitude. That magnitude determines its exact spot on the number line.
And measurement, that sounds like, the ability to actually pin it down, to start and stop, delineate boundaries.
Yes, exactly. Measurement is the ability to contain and articulate that magnitude. If I can start counting and finish counting.
Whether it takes a second or a billion years.
Right. If I can perform that act of quantifying, that's measurement. A number is something that can be precisely placed on that number line, even pi, right? Digits go on forever, but its value is defined. It answers how many or how much with certainty.
Okay, this feels really important. This is the critical distinction we need to keep in mind. Numbers, certainty, position, magnitude.
Yes. And when we talk about the concept that deliberately breaks all those rules, well, that's when we bring in the symbol.
The infinity symbol. Looks like a figure 8 on its side.
That's the one. It's iconic, right?
Yeah.
But fundamentally, that symbol represents a concept, a state. It does not represent a value.
It's the placeholder for.
Boundless.
Undefined.
Exactly. And the second we step away from definable magnitude and fixed measurement, we're not talking about numbers anymore. We've entered the realm of mathematical concepts.
All right, so we've established the pretty strict entry requirements for being a number. Now let's formally look at the challenger, infinity. If it's not a number, what is it doing in mathematics? Why do we need it?
Well, according to our analysis of the sources, infinity isn't defined as an answer in itself. It's defined as an idea.
An idea?
Yeah, an idea we use to solve or at least address certain, well, let's call them existential mathematical questions. Questions that bump up against boundaries.
Existential mathematical questions. Like what? Give me an example.
Okay, think about the ones that test the limits of our sequences. Like, what's the absolute highest number we can possibly count? Is there one?
Doesn't seem like it.
Or where does a number line truly end?
Again. Seems like it just keeps going.
Or maybe what happens to how fast a function grows if its input just gets bigger and bigger without any limit?
Ah, okay. So questions about no limit.
Exactly. And the source material tells us the standard answer, or maybe the label we use for those situations, is infinity. It's the designation for something absolutely fundamentally without limits.
Okay, so that leads straight to the core definition we pulled from the sources. Infinity is an endless quantity that possesses no magnitude or dimensions.
And that's the ultimate contrast, right? To our definition of a number, which must have magnitude and must be measurable, infinity has neither.
No dimensions. That's interesting, too.
Yeah, it's not just sizeless in quantity, it's dimensionally undefined in this context.
We also need to clarify, based on the sources, that infinity isn't just one single concept, is it? There's a duality.
Right. It has a dual nature, and it's tied directly to how we visualize numbers on the number line. We talk about both positive and negative infinity.
So it's not just infinitely big. It can also be infinitely small. Or maybe infinitely negative.
Kind of. If you keep counting up, adding positive numbers, you're heading conceptually towards positive infinity. We write that as in 50 all.
That's the one on the right-hand side of 0 on the number line, the theoretical biggest.
Right. The conceptual maximum, though you never reach it. And if you keep subtracting, heading left from 0, you're conceptually moving towards negative infinity. That's in 50 a liar.
The conceptual minimum.
Exactly. Both are concepts. Both represent endless continuation, just in opposite directions. Neither is a specific place you can land on.
Okay, let's dig a bit deeper into this idea of endless, because that feels like the absolute key characteristic here. The sources really hammer this. Infinity has no end. It is, by definition, boundless.
It's not just a really, really big number. It's the quality of having no defined boundary whatsoever.
The sources used an analogy? Something about a journey.
Yeah, like picturing a journey where you're trying to reach infinity. You can't. You never arrive.
Because there's no there.
Exactly. When there's absolutely no mathematical or physical reason for something to stop, whether it's the sequence of integers or maybe theoretical time duration or a geometric path, we label that state as endless. Infinity is perpetually beyond our grasp.
It's the ultimate always further. And this loops back perfectly to the number line we talked about earlier.
Right. We know the numbers themselves go on and on indefinitely, stretching out towards positive and negative infinity.
So the numbers are limitless in quantity, but infinity is the conceptual label we slap onto that state of being limitless.
That's a crucial distinction. It's a boundary condition we use to describe the set of numbers, but it's a boundary that can never actually be reached. You can only approach it asymptotically.
So when mathematicians talk about the set of real numbers, they might say it approaches infinity.
But they'd never say the number line contains infinity as one of its points.
Yeah.
It's a property of the set, not an element within the set.
Okay, here's where it gets, I think, really interesting, and where we tackle that core misconception head on. We've set up what a number is measurable, quantifiable value. Now we pivot to the number one reason infinity fails the test.
Which is the absence of quantity.
Right. That's the critical distinction, isn't it? A number tells you how much or how many slices of pizza are left, what the temperature is. It denotes a quantity.
But infinity, by its very definition, denotes the exact opposite. It signifies the absence of a quantity.
It describes a state of affairs, not a fixed measure.
Exactly. It's not a specific numerical value you can write down. It implies continues indefinitely. It's a description of behavior.
I think we really need to linger on this for a second because it feels like the absolute heart of the argument. It's the difference between saying, I have 50 trillion grains of sand, which is a huge quantity, but still a quantity.
Still fine with me.
Versus saying, the potential number of grains of sand is endless. One's a number, the other's a concept about limits.
And you can't just plug that concept into standard arithmetic like you can with the 50 trillion.
Which leads directly to the second big contradiction, right? Infinity cannot be measured or quantified.
The sources are crystal clear on this. Infinity is not a real number. Think about it. If something has no beginning and no end, how on earth can you measure its length or its magnitude?
You can't put a boundary around it.
It can't. If we try to quantify it, like, okay, let's pretend infinity is x, and let's say x equals, I don't know, 10 to the power of a billion.
A massive number.
Huge. But then what happens if we add 1 to it?
Then you get 10 to the power of a billion plus 1, which is bigger.
Exactly.
Yeah.
So our original x wasn't truly boundless after all. We immediately violated its nature by giving it a value.
Okay, yeah. That makes sense. The act of quantifying it destroys its defining property.
Precisely. Quantification needs a fixed start and a fixed end. Infinity inherently lacks both. It is the essence of boundlessness.
Now, this is the bit where I think a lot of people, myself included, sometimes get tripped up. We tend to think of infinity as just a really, really big number, like the biggest one imaginable.
It's a natural way to think, but it's misleading.
We have to really stress this point from the sources. Even though the set of numbers is limitless, there's no biggest number. The concept of infinity isn't considered one of those numbers.
If it were a number, it would have a defined place. It would have to follow the rules of arithmetic, but it doesn't.
Okay, now let's get to what feels like the most paradoxical, maybe even philosophical point from the sources. It touches on the nature of math itself. It's the concept of completeness.
Ah, yes. The idea that infinity does not increase, infinity does not grow.
This sounds completely counterintuitive. How can something that's defined as endless and that goes on, how can it not be growing?
This is a really subtle but crucial distinction. It requires a bit of careful thought. The sources describe the concept as being already complete.
Already complete.
Yeah. So while we say it goes on, which sounds like progress, like a journey, the concept itself, its state of being boundless, is static.
The source material said something like, it does not do anything. It simply exists.
Exactly. It exists as a designation for that state of utter completeness in terms of boundlessness.
Let's try to unpack the implications of that completeness. If I have a finite number, say 10, adding 1 makes it 11. It grew, right?
Yeah.
By 10%.
Clearly, it increased.
But if infinity could grow,
Yeah.
wouldn't that imply the original infinity wasn't actually maximal? Like there was a bigger state it hadn't reached yet?
You've hit the nail on the head. That would contradict the fundamental definition of infinity as being absolutely boundless.
If it's already representing the absolute maximum possible state of endlessness, you can't add to it.
You can't. Adding 1 to infinity, well, it must still just be infinity. If you could increment it, making it infinity plus 1, then the infinity you started with wasn't truly infinity. It was just a very, very large number pretending to be infinity.
Okay, so if I start counting integers, 1, 2, 3, and I say the count is progressing towards infinity.
The process of counting is dynamic, yes. It's progressing.
But the conceptual destination, the state called infinity, is static. It's already 100% boundless. It's like a finished state of not being finite.
It doesn't become bigger because it already represents the state of maximal boundlessness. It's a state of being, not some dynamic quantity you can add to or subtract from using normal rules.
And this impossibility of growth just cements its status as a concept, not a number. Because it breaks a fundamental rule of arithmetic, doesn't it?
It breaks the rule that for any number, $6 plus platinum must be greater than $6. Infinity doesn't obey that.
The moment you try to measure it or do standard math on it, you impose finite boundaries.
And the concept collapses. It just becomes a stand-in for a very large number again.
So to stay infinity, it has to remain untouchable by measurement, quantification, or standard algebra. Wow. All right, if our sort of intuitive grasp is that infinity is non-growing and non-quantifiable, how did mathematicians, especially more recently, formalize that? We need to move beyond just counting things and into the more abstract world of set theory.
Yeah, this is where it gets a bit more technical, but also, I think, really brilliant. This comes largely from Georg Cantor's work in the late 19th century.
Cantor, right.
He realized mathematics needed a formal way to define infinite that didn't just rely on waving your hands and saying it goes on forever.
Yeah.
It needed a definition based on the internal mathematical properties of the set itself.
Okay, so what is the formal technical definition of an infinite set in this context? Let's take this slow, make it clear for the listener.
Okay, so the sources give us a definition that really changed the game. An infinite set is defined as a set that can be put into a one-to-one relation.
One-to-one relation.
Between the set itself and a proper subset of the set itself.
Whoa, okay, that sounds dense. One-to-one relation between the set and a proper subset of itself. Can we use an analogy, maybe, to make that tangible before we hit the numbers?
Absolutely. The classic thought experiment here is Hilbert's Hotel. It illustrates this perfectly.
Hilbert's Hotel, okay.
Imagine a normal hotel, finite number of rooms, let's say 100 rooms, and it's completely full. Every room has a guest.
Right, no vacancy.
Now, a new guest arrives. What does the manager have to do?
Turn them away. Sorry, we're full.
Exactly. That's the nature of a finite set. It's full. The original set, 100 occupied rooms, cannot map one-to-one onto the new set, 100 rooms plus one new guest, without someone being left out.
Makes sense. Finite means limited capacity.
Okay, now imagine Hilbert's Hotel. This hotel has an infinite number of rooms, numbered 1, 2, 3, 4, and so on forever. And just like before, it's completely full. Every single infinite room has a guest.
An infinitely full hotel, okay.
Now, a new guest arrives. Does the manager turn them away?
Based on where this is going? Probably not.
Correct. Instead, the clever manager makes an announcement. Could the guest in room 1 please move to room 2? Could the guest in room 2 please move to room 3? Guest in room 3 to room 4.
So every existing guest just moves one room down. The guest in room 1 moves to room +1.
Precisely. Every single one of the infinite guests shuffles down one room.
And what does that achieve?
Well, think about it. Are all the original guests still in the hotel?
Yeah, they just moved rooms. Nobody left the hotel.
Right. But what about room 1?
Room 1 is now empty.
Exactly. Room 1 is vacant, so the new guest can check in. The hotel accommodated the new guest, even though it was already full.
Wow, okay. So how does that connect back to the definition?
The original set of guests, the infinite set dollar, was put into a perfect one-to-one correspondence with a proper subset of itself.
Which subset?
The set of all rooms numbered 2, 3, 4, and onwards. That's a proper subset because it's missing room 1. But the mapping worked. Guests from room 1 went to 2, 2 to 3, etc. The infinite set mapped perfectly onto a part of itself.
And finite sets can never do that. If you take away an element from a finite set, the subset is always smaller. You can't map the original set onto it one-to-one.
Precisely. This paradoxical ability is the defining characteristic of an infinite set in set theory.
That's actually really elegant. It perfectly captures that weird does not grow property we talked about.
Yeah.
Even though the subset, guests in rooms 2 onwards, is technically smaller because it's missing the room 1 guest's original position, the total count of guests is still infinite. The hotel didn't run out of space.
Right. The cardinality, the size of the infinite set, remained unchanged even when mapped to a part of itself.
And this strange behavior, this rule breaking, it shows up when we try to apply normal arithmetic, doesn't it? The sources had an algebraic example.
Yes, the equation, sex, x plus n dollar, where $1 is any finite constant, like 1 or 500 or whatever.
Okay, let's look at 6x plus n dollar in normal math with finite numbers. This is wrong, isn't it? If 1 isn't 0.
It's impossible. If $6 is, say, 10 and new dollars is 2, you get $10 pen plus 2, or $10 is 12, 2. That's false. For finite numbers, $6 is always less than 6 plus n dollar if n is positive.
Addition means increase in the finite world.
Exactly. But the sources explain that this relationship, 6x plus n dollar, is only possible, only holds true, when $6 represents an infinite quantity.
Because adding a finite amount to an infinite quantity doesn't change the fact that it's infinite.
Yeah.
The result is still conceptually the same infinity.
It doesn't grow. It reinforces the point from earlier. This single equation, which is nonsense in finite arithmetic, demonstrates perfectly how the concept of infinity operates outside those standard rules.
Adding, subtracting, multiplying by finite numbers, none of it changes infinity's essential state of being infinite.
And that formal definition, based on set theory and its implications like 6x plus n dollar, is really the ultimate nail in the coffin for infinity being a real number.
Because if something doesn't follow the basic rules, the axioms of addition and inequality,
it simply cannot function as a standard numerical value within that system. It forces us to classify it differently, not as a number on the number line, but as a specific type of cardinality, a measure of the size of a set, even an infinite one.
And it's worth just quickly mentioning, Cantor didn't stop there, did he? He found different sizes of infinity.
That's right. He showed that some infinite sets are bigger than others. There's countable infinity, like the integers. You can list them 1, 2, 3, even though it goes forever. That's the size of Hilbert's hotel guests.
And then there's uncountable infinity.
Like the set of all real numbers, all the points on the number line, including fractions and irrationals. He proved you cannot list them all in a sequence, even an infinite one. There are fundamentally more real numbers than integers.
So even within the concept of boundless, there are different levels, different orders of infinity.
Yes, different infinite cardinalities. But crucially, none of them are finite numbers. They're all measures of infinite sets, not measurable quantities themselves.
Okay, so we've established infinity as this concept, this state of boundless completion, formally defined by set theory. Now let's circle back and really hammer home the contrast with what most people think infinity is just a really, really, really big number.
Yeah, this is probably the most common point of confusion, and it's understandable because the scale of truly large finite numbers is already hard to grasp.
Our everyday experience just doesn't prepare us for it.
Not at all. So we need to draw that line clearly, show just how immense some defined finite numbers are, and yet how they still fall infinitely short of infinity itself.
And the classic starting point for gigantic but still finite numbers is the googol.
The googol, defined as 1 followed by 100 zeros, or 10 to the power of 1.
10 to the power of 100. How big is that in context?
Well, think about the estimated number of atoms in the entire observable universe. That number is thought to be somewhere around 1001 hell, followed by about 80 zeros.
So a googol with 100 zeros is already significantly larger than the number of fundamental particles we can even see.
Way larger. Yet, and this is the key, it's utterly, completely finite. You know exactly how many digits it has. 101, the 1 in the 100 zeros. It represents a precise quantity.
You could, in theory, count up to it, given an absurd amount of time and resources. But it's countable. It has an end.
Exactly. But wait, we can go bigger. Much, much bigger, as the sources remind us.
Ah, yes. Time for the Googolplex. This one always bends my brain a bit.
It bends everyone's brain. The Googolplex is defined as 1 followed by a googol zeros.
Wait, not 1 followed by like 200 zeros.
Yeah.
1 followed by 10 to the power of 100 zeros.
Yes. The number of zeros is 10 numbers. So the number itself is $10, or
So-
$10, $10. Okay.
Yeah.
Visualizing that is impossible.
Pretty much impossible in any physical sense. Remember how a googol $10 was already bigger than the number of atoms in the universe?
Yeah.
Now imagine trying to write down the Googolplex. You need to write 10 zeros. If you tried to assign 1 0 to every single atom in the known observable universe...
You would run out of atoms long before you wrote down all the zeros. Long, long, long before. You wouldn't even make a dent. There isn't enough matter, enough energy, enough space, enough anything in the physical universe to actually write down or store the number Googolplex in its full decimal form.
It's physically unrealizable. You couldn't write it down.
Correct. And yet, this is the profound point about these giant finite numbers. Mathematically, the Googolplex is perfectly well defined. It is a number.
It's quantifiable, even if we can't physically quantify it.
Exactly. If you had an infinite amount of time and infinite resources, which is borrowing from the concept we're discussing, you could theoretically count up to it. It lives firmly on the finite, measurable side of the mathematical fence. It has a specific value.
But even the mind-bending Googolplex, it's not the end of the line for big numbers, is it? The sources mention this. People sometimes call it the largest number, but that's not quite right.
No, it's not strictly true, because mathematicians can always define larger ones. The process itself is unbounded.
The sources specifically mentioned Graham's number.
Graham's number, yes. We don't need to get into the weeds of how it's calculated. It uses this incredibly powerful notation called Knuth's up arrow notation, basically nested towers of exponentiation.
Sounds complicated.
It is. But the key takeaway is this. Graham's number is so mind-bogglingly enormous that the number of digits in Graham's number makes the entire Googolplex look like, well, like zero, practically.
It dwarfs the Googolplex to an unimaginable degree.
Completely. It defies not just physical storage, but even writing it down using powers of 10 is basically impossible. You need the special notation.
So the reason for bringing up Graham's number, based on the sources, is just to emphasize that we can keep going. Mathematicians can define finite numbers far, far larger than we can even describe easily.
Exactly. The capacity to define immense yet still finite quantities is essentially limitless. The numbers get bigger, the definitions get more complex, but they remain defined. They remain finite.
And this is the critical distinction we have to keep highlighting. Googol, Googolplex, Graham's number. These are all numbers, vast, immense, maybe physically impossible to represent, but they are quantities. They are measurable, they are quantified.
You could, in principle, place them on a number line, even if that placement is incomprehensibly far from zero. They denote a specific, albeit enormous, value.
Whereas infinity.
Infinity is non-quantifiable existence. It's not just another huge number waiting at the end of the line that you could eventually reach. It is the conceptual state of having no line, no end, no boundary at all.
The difference between, say, $10 and 50 isn't just size. It's fundamental nature.
It's the difference between finite existence, no matter how vast, and pure measureless idea. One is a value, the other signifies the complete lack of a limiting value.
Okay, so we've established pretty firmly, infinity isn't a number. But we use the concept and that infinity symbol all the time in NAS, don't we?
Constantly. You can't just punch infinity into a standard calculator and expect an answer. But the idea of infinity is a necessary descriptive tool.
How so? How does it actually get used in practice if it's not a value itself?
It's used to clarify the behavior of things, sequences, systems, geometric lines that simply don't terminate. They don't have a finite end. The sources gave 3 really good, tangible examples.
Right. Let's walk through those. Example 1 was about decimals.
Infinite decimals, yeah. Okay. Which can come from perfectly simple division problems.
Like the classic example. Divide 2 by 3.
Exactly. You punch that into a calculator or do the long division, and what do you get?
You get 0.66666. And those sixes just keep coming. They never stop.
Right. And that's a perfect application of the concept of infinity. The number itself, 2/3, is perfectly well defined. It's finite. It's measurable. It sits at a specific point on the number line between 0 and 1.
Okay, the value 23 is fine.
But its decimal representation is endless. To describe that, we need the concept of infinity. The conclusion isn't that the answer is some infinitely large number. The conclusion is that there are an infinite number of 6s after the decimal point.
So the infinity symbol, or the idea behind it, acts like a shorthand here. It just means this pattern repeats forever, or does not terminate.
Precisely. It's the tool we use to describe that ongoing, non-stopping process that arises from the division.
Okay, that makes sense. What was example 2? Something about the number line itself.
Yeah, going back to the number line framework we introduced earlier, how do we describe its full extent?
Well, we observe it. Numbers going right, getting bigger and bigger. Positive integers, fractions, irrationals.
And going left, getting more and more negative.
Right. It seems to just stretch out forever in both directions.
And how do we describe that stretching out forever? We say the line stretches towards positive infinity on the right and towards negative infinity on the left.
So infinity here acts as the theoretical endpoint.
Or maybe.
The lack of an endpoint.
Exactly. It explains that the set of real numbers doesn't just abruptly stop somewhere, like at a trillion or a Googolplex. The potential for numbers continues indefinitely.
It's the ultimate conceptual boundary marker. But again, it doesn't mean there's a point labeled infinity that you can land on.
No. It means the process of assigning numbers, of moving along the line, can continue without end. It describes the boundless nature of the real number system itself, even though those ends are perpetually unattainable concepts, not locations.
Okay, got it. Decimals, number line ends. What was the third example from the sources? Geometry.
Yes, geometry. Specifically, the concept of parallel lines. This shows a slightly different, more abstract application.
Okay, Parallel lines. In basic Euclidean geometry, the kind we learned in school, what's the rule?
Two parallel lines, by definition, never meet. They maintain the exact same distance apart forever.
They run alongside each other infinitely, never intersecting.
Right. But the sources mention another branch, or way of thinking, called projective geometry. It handles things a bit differently, often for theoretical elegance.
And how does projective geometry treat parallel lines?
Well, in certain formulations of projective geometry, mathematicians find it useful to define things so that all lines intersect somewhere. To make this work, they say that parallel lines don't just never meet. Instead, they meet at infinity.
Whoa. Okay, so infinity becomes a theoretical place, a point of convergence way out there.
Sort of. It's often visualized as a point at infinity, or sometimes a line at infinity added to the standard geometric plane. By adding this conceptual element, theorems can sometimes be stated more simply or universally. For example, any two distinct lines in the projective plane intersect at exactly one point.
Even if those lines were parallel in the normal view.
Yes. In this framework, their intersection point is considered to be at infinity. It's an abstraction, a conceptual location far outside our measurable finite Euclidean space. It represents the theoretical point where paths that never meet in finite space would conceptually converge. It helps unify the geometry.
Okay, that's fascinating. So whether we're talking about repeating decimals, the unbounded number line, or even where parallel lines meet in abstract geometry, infinity isn't the answer itself.
No. In every case, it's consistently used not to represent a specific numerical value or quantity, but to describe a state of being endless, boundless, or non-terminating.
It's an explanatory concept.
Yeah.
A necessary tool for talking about things that don't have finite limits.
Exactly. It's the label we put on the idea that a set or a sequence or a process or even a theoretical geometric path just doesn't have a finite boundary or starting point. It describes the behavior of mathematical objects without actually being one of those objects itself. #tag outro.
Wow, okay, we have really covered a lot of ground there. A deep, comprehensive dive into the nature of infinity, all based on your source material.
We definitely went through the key arguments.
We started by defining what a number has to be. Measurable, quantifiable, possessing magnitude.
Right, the entry requirements for the number club.
And we established pretty clearly that infinity, because it represents the absence of quantity, the state of pure boundlessness, it fails that test completely.
Yeah, it's fundamentally disqualified from being a real number.
We confirmed it's this boundless, non-growing concept. I like that phrase from the sources, that it's already complete.
That's a key paradoxical idea, yeah.
And we saw that the huge difference between, say, an unimaginably large but finite number, like $10 text Google.
And the concept isn't just size.
It's a difference in kind.
Yeah.
Finite existence versus pure, non-quantifiable idea.
A value versus the lack of a boundary.
We also touched on that more complex but powerful set theory definition from Cantor. Infinity being the unique property of a set that can map one-to-one onto its own proper subset, like Hilbert's Hotel.
Which mathematically captures that paradox we kept coming back to, the fact that adding 1 to infinity conceptually doesn't make it any bigger.
Right, and that actually leads perfectly into the final thought we wanted to leave the listener with, something to kind of chew on maybe.
Yeah, something that ties that intuitive paradox back to the formal math and maybe makes us question things a bit.
We spent some time on that weird equation, the one that's impossible in normal math. Sexexel's end goal, where $6 is infinity and others is some finite number.
Right. Infinity plus 1 equals infinity. Infinity plus a billion equals infinity.
So if that identity holds true for infinity, what does that really say about the basic operations we just take for granted, like addition?
Yeah, think about it. We fundamentally define addition, at least with positive numbers, as an act of increase. When you add a positive quantity to a finite number, its magnitude increases. It gets bigger.
Always. 6 plus A is always greater than $6 for positive number.
But infinity just ignores that law. It defies it completely. So does that force us to reconsider what addition or subtraction even is? Are they just functions that only really work properly in the finite world?
Are they? Maybe. Constructs tied entirely to measurable quantity. Constraints of finite space rather than universal truths that apply across all possible magnitudes, including the infinite.
Does infinity's rule-breaking behavior imply that our everyday arithmetic is, in a way, limited? That the tools perfectly suited for counting apples or measuring distances simply break down when faced with the concept of truly boundless existence?
It really makes you question the foundations, doesn't it?
Yeah.
How deep do those rules of arithmetic actually go?
It definitely pushes the boundaries of mathematical thinking.
A truly thought-provoking place to leave it. Thank you so much for sharing these incredibly rich sources and walking us through this exhaustive deep dive into the nature of infinity. It's been fascinating.
My pleasure. It's a mind-bending topic, always good to explore. Until next time.